Welcome back. We're still in section 4.1. We're learning about rational functions, and now we're going to learn how to graph some of them. Let's take a look. What's helpful is to write it in this form that they give here, negative x to the 7th plus 1. And here are the steps in graphing it. Okay. This is the graph of x to the 7th. So the basic way that you know this is that, let me draw a couple in here. X to the odd power is always going to look like this. It goes through the point 1, 1. It goes through the origin, 0, 0. And it goes through the point negative 1, negative 1. As the power gets bigger, remember in the previous video we said it gets steeper. So instead of this kind of gentle curve, it'll do something more like this. That's a really bad drawing, sorry. So it still always goes through the points 1, 1, 0, 0, and negative 1. It's just that instead of sort of going off like this, it goes very steeply down. And here it's going to quickly flatten out and then steeply come up. It's a subtle distinction. It's just instead of, let me clear out these and sort of draw again to make the point. Instead of a sort of gentle this, you get a more steep kind of this, where it's both more vertical here and more flat here. So this is a large odd power, and this is a small odd power, like the third power. Okay, for the power of 1, we get lines, and we know how to graph those. So that's why in this example we've started off with the graph of x to the 7th. It's a fairly large odd power, so it's fairly flat bits here and fairly steep bits away. Okay. Whoops, sorry, let me get rid of those pen marks. But we don't just have x to the 7th, we have negative x to the 7th, and we know that is a reflection across the x-axis. So we change the graph to look like this. We reflect across the x-axis. Now I have the graph of negative x to the 7th, but I want negative x to the 7th plus 1, so the only transformation left to do is shift it up by 1. And the 3 points we had, okay, we started with these as our known points for any odd power, but when I do the reflection, this went here, this went here, so I made the y-coordinates negative, and now I just shift them all up by 1 unit. So instead of negative 1, 1, I have negative 1, 2. Instead of 0, 1, we have 0, 1. Instead of 0, 0, we have 0, 1. And instead of 1, negative 1, we have 1, 0. It just shifted everything up. OK, how about this one right here? So now notice we have an even power of x. So let's ask, what do even powers look like? Well, here's the parabola x squared. It's supposed to come down and actually touch there. As you get larger power, it gets steeper and flatter. Okay, it's still going to go through the point negative 1, 1, 0, 0, and 1, 1. But this would be like x to the 4th. It's a bit more vertical as you move away and a little more flat as you get to the center. And if you put in a large power like x to the 12th, say, you still go through these points, negative 1, 1, 0, 0, and 1, 1. But it's really, really, really vertical, and then it flattens out very, very, very much, and then it's really, really, really vertical. Okay, it almost starts looking square-like. It flattens out so much there. So those are the graphs of your generic even powers. Okay, and you can play around with a graphing calculator or a graphing program. So what about this one? Well, we're going to start with x to the 6th. That's pretty flat. Then we have x plus 1 in parentheses, and that is a left shift by 1 unit. So we take this graph with its standard reference points, negative 1, 1, 0, 0, 1, 1, and I shift the x-coordinates left. But now I have a vertical compression, so I take all those y-coordinates and I multiply them by a half. So instead of negative 2, 1, I multiply the y by a half, and I have negative 2, half, etc. So it's even flatter. So how are we going to identify what are called the zeros of a polynomial and what is called their multiplicity? Well, a 0 is just where it has a value of 0. Okay, whoops, sorry. And the axis is exactly given by the equation y equals 0. So these points are where y is 0. Solve the equation y or f of x is 0. Using what the book calls the zero product property, I just call it factoring. So if you have a factor polynomial, and we'll see how to do that later on, it's a fairly large topic in this section, how to factor polynomials, in this chapter, sorry. If you plug in a certain number and you get out a 0, that's called a 0 or a root. Okay, root is more common terminology. It's a root of the function. It also means that's an x-intercept because you're getting out y equals 0. What's equivalent to having r is a 0 is that x minus r can be factored out of f, okay? Or f of r equals 0. These are all the same thing. If f of r is 0, then you factor out x minus r. And if x minus r can be factored out, well, then x minus r is 0. And we'll see how this plays out in examples. Okay. So can you find a function, polynomial, of degree 3 whose zeros are -1, 2, and 3? So f of x is going to be written as a polynomial. Now, since -1 is a 0, aka a root, that means that x minus -1 or x plus 1 is a factor. So if the other roots are 2 and 3, what are the other factors? So I can factor out this x plus 1 and also factor an x minus 2 and an x minus 3. So this has now been expressed to have a root of -1, a root of 2, and a root of 3. And notice, if you plug in f of -1, you get 0 times whatever. I'm going to get out a 0. If you plug in f of 2, you get out something times 0 times something, and you're going to get out a 0. And similarly, if you plug in 3, you get out something times 0, and all of these are going to produce zeros. So what I have now is I definitely have a function that has these as the zeros. Okay. Why is this a polynomial of degree 3? Notice I have 3 terms involving x. If I expand all of this out, it'll take some work, but eventually I'll have, whoops, wrong button, sorry. I want it to be on laser pointer. I will have an x times an x times an x. That gives me an x cubed. I'll also have things like 1 times x times -3 or x times -2 times x. But I get a bunch of things out. The most x's I can get are x times x times x, which gives me my x to the third. So it's a degree 3 polynomial. So I will end up with an x cubed plus some other stuff. And eventually I'll have a constant term, which is actually just going to be a +6. I'm going to clear all of this out, copy this down if you want, because now I want to go through the book solutions. Okay. So remember, again, if r is a 0, x minus r is a factor. So x plus 1, x minus 2, x minus 3 are factors. Therefore, it can be written like this. We do have the option of multiplying by some number out here if we want. It's not going to change the fact of where we get out zeros. Okay. We can change a, and that causes a stretch or compression or reflection, but it's not going to change the intercepts. Again, if one of these things spits out a 0, then I get 0. It doesn't matter what a is. Okay, so let's graph it with a as 1. This is exactly what we had on the other slide, x plus 1 times x minus 2 times x minus 3. Okay, and there it is if you plug it into a calculator. Notice here is the intercept of x equals -1. Here is the root x equals 2. Here is the 0 of x equals 3. I'm just using various terms interchangeably because they all mean the same thing. X-intercept versus root versus 0 of the function. Okay, that was my phone, not yours. Sorry. Okay. So when we're talking about roots of a polynomial, there's something that comes up called multiplicity of root. So for example, in this polynomial, okay, what are the roots? What are the zeros? 0 is, because here is x minus 0, but it's being raised to the third power. And if you have one of these factors with a power on top of it, it tells you what is called the multiplicity of the root. So because I have an x minus 0 to the third power, 0 is a root of multiplicity 3. So now, looking at these other factors, what are the roots and what are their multiplicities? So 5 is a root of multiplicity 1. This term x minus 5, you can definitely imagine it having an exponent of 1 up here. But what about that last term? There, negative a quarter is the root, and it's of multiplicity 4. Okay, so we'll come back in the next video to talk about graphing a polynomial using its intercepts.